Good afternoon, everyone. It's on mute. Let's continue with our topics of resistive circuit analysis. Today we look at superposition, and then we'll wrap up by introducing the concept of Thevenin and Norton equivalent circuits. Okay. So we've covered mesh current analysis, we covered node voltage analysis. Then we looked at special cases where we can apply and create a super node and a super mesh. So staying on theme of super, we have a technique known as superposition principle. Well, superposition principle is basically allowing us to break up our circuit or circuit analysis into multiple pieces. Okay. So superposition is a technique where we analyze a circuit by simplifying it into multiple pieces, sort of like individual modules. Okay. Now, recall that the simplest of techniques is where we can take where a circuit only has one single source and we reduce all the resistors in that circuit down to one single equivalent resistance, right? So let's say you had more than one source. Let's say you had two voltage sources, for instance, or for example. Then we cannot do that. We cannot simplify it all the way down to one single resistance, right? Because we cannot negate the other voltage source. So we apply node voltage or mesh current analysis. Well, superposition allows us to break it up into two separate circuits. For two sources, you have two separate parts, and each piece is analyzed independently of the other one. And at the end, we simply add up the results from both analyses. Okay. So simply stated, superposition allows us to break up a circuit into n number of pieces depending on n number of sources. So if you have three sources in a circuit, you can break it up into three different circuits. If you have five, you break it up into five different pieces and analyze each piece separately. So the reason we can do that is because of the superposition principle. The superposition principle states that if you have n sources in a circuit, then the voltage and or current at any point in a circuit is a result of all of those n sources working at the same time. Okay. So if it's a result of n number of sources working at the same time, it stands to reason that if you break it up into n number of parts with only one source working at a time, you can take those voltages and those currents, add it up, and determine your final answer. And that essentially is the superposition principle. We analyze with only one source active at a time. We reduce all other independent sources in the circuit to zero. Reducing a source to zero means replacing it with either a short circuit or an open circuit. And I will explain. What is the property of a voltage source? The property of a voltage source is that it will supply its rated voltage between its terminals, irrespective of what is connected to those terminals. Meaning VAB will always be equal to Vs. If we wish to reduce Vs to zero, it means that both VA and VB are the exact same potential. So in order to do that, the only way to do that is if both VA and VB were connected together. So we replace we replace the voltage source, independent voltage source, with a short circuit. If you replace it with a short circuit, VAB is equal to 0. And so that's what it means. So we can technically call it reducing a source to 0, means replacing the voltage source with a short circuit. Make sense? Right? Similarly, for a current source, if you want current to stop flowing, if you want current to be reduced to 0, meaning you want it to stop flowing, the only way we can do that if there is no pathway for the current to flow through. So we replace a current source with an open circuit. And so not quite an oval. Let's say you have a current source IS connected between A and B. If we want to reduce, so current IAB is equal to IS, obviously, between those terminals. If you want to reduce the current IS to 0, we simply replace it with an open circuit. And so IS is now reduced to 0. Okay, and that's the principle, or that's the concept behind reducing sources to 0, meaning replacing it with an open circuit or a short circuit. So far, so good. Okay, so that's what this means. And SC and OC are my shortcuts, acronyms for short circuit and open circuit. Okay, so if you have n number of sources in a circuit, we analyze a circuit with only one source active at a time. All other independent sources are reduced to 0. Reducing a source to 0 means replacing a voltage source with a short circuit and a current source with an open circuit. Once you have only one source, then you can possibly simplify your analysis by either reducing all the resistors down to one single resistance and applying simple analysis techniques, or you could apply node voltage and mesh current also. But that would kind of rather defeat the purpose of doing superposition. The whole point of doing superposition is so that we can apply simple resistive techniques or resistive analysis techniques. All right, questions? Any questions? Okay. All right, let's look at an example. As far as examples go, this is rather simplistic. Just has two sources and two resistors. It shows three resistors, but R2 and R3 are in series, so you can automatically combine them. So determine current I2 using the principle of superposition. I2 is already noted in the circuit diagram. It's coming from the top, and it's flowing through R2 and R3, right? So first thing I'm going to do is I'm going to combine R2 and R3 into one single resistor. This is given as 10 volts. IS is 2 amps. This is 5 ohms. This is 2 ohms. And this is 4 ohms. Okay. So let's do coming down. Let's call this R4. R4 is equal to the series combination of R2 and R3. So 5 ohms, Vs is 10 volts, Is is 2 amps, and R4 is what, 6 ohms. All right. Now, the current I2 remains exactly where it is. That doesn't change. Okay. So how many pieces can we break the circuit into? How many sources do you see in the circuit? Two. How many pieces? Two. Two separate analyses. Okay. So you have to perform two separate analyses to determine I2. So let's do this first. Vs active and Is is equal to 0. If Vs is active and Is is equal to 0, this becomes a rather straightforward example. Now what I'm going to do is I'm going to call Is due to Vs with a subscript of, sorry, not Is, I1, I2. Okay, that's what we need to find. So I2 in this case shall be referred to as I2 Vs. Additional subscript notation, just indicating that this is I2 due to the Vs source being active. So my circuit comes like this. That's it. Is is open. Is is reduced to 0. And all we have in here is R4 6 ohms, R1 5 ohms, and Vs of 10 volts. So what is I2 Vs? What is it? Anyone? Absolutely. 10 divided by 11. How much is it? Approximately equal to 0.909 amps. Is everyone in agreement? Yeah. 11 times 0.909 is 9.999 something. So 0.909 amps. All right. As far as things go, rather straightforward. Again, simple example. How about now we have Is active and Vs is equal to 0 volts. I2 is now referred to as I2 due to Is and the exact same circuit. So I'm going to copy it out here. Vs is now 0 volts. Replace it with a short circuit. And Is What is IS? How much is IS? 2 amps. So what technique can we use to determine the current I2? We have two resistors. So if I redraw the circuit, I can draw it like this. One current coming down. All three of them are in parallel, right? 2 amps, 6 ohms, and this is 5 ohms. The 5 ohm resistor is now in parallel with the current source because this end is now connected. This end is now connected to this bottom end right there. Does everybody see that? Okay. So that renders all three components in parallel. If everything's in parallel, what happens to that current? Current's coming down. Some of it goes this way, some of it goes this way. What is happening to that current? It's getting divided. What technique can we apply? Current division. Current division is a shortcut. Alternatively, you could apply just the resistive analysis techniques, meaning you have two resistors in parallel, reduce it to one single resistance, determine the voltage across those two terminals, right? So you could reduce 5 and 6 in parallel to one single resistance. Then you could apply Ohm's law to find the voltage between those two nodes. Once you have the voltage between the two nodes, again, apply Ohm's law to 5 ohms and 6 ohms, and you find the current in each branch. But current division is a shortcut, allows us to find the current directly. So if I look at 2 amps, I want to find the current going through the 6 ohm resistor. First of all, what is Req between the two resistors? Remember, we need Req, right? So I 6 ohms is equal to a fraction of 2 amps. The fraction is given by Req, which is 5 times 6 divided by 11. This would be divided by 6 ohms. 5, 6 are 30. How much is this current? Anyone? How much does it come out to be? It is 0.909. Wonder of wonders. 0.909. So what is my eventual I2 value? I found I2 due to VS. I found I2 due to IS. Superposition principle is we break it up into individual pieces. Once we find individual parts, we need to sum it up again, right? So we had one single quantity, we broke it up. Now we have to join it together. So what is my actual I2? .909 plus 0.909, right? That is the principle of superposition. Do we all agree? Take a pause, think over it. Let me know if you have any questions. What answer do we have? 1.8. 0.818. That would be correct if the current source was pointing in the upwards direction. But if you look at the current source, it's pointing down. If it's pointing down, the current coming from the source is actually going up in this direction. I2 is given to us as coming in this direction. And so I2IS is the opposite due to the current source pointing down. And so the 6 ohm resistor current is 0.909, but I2IS is pointing in the opposite direction. So it's equal to minus the 6 ohm resistor we found. It's minus 0.909. And the sum total, the result, is 0. All right, let's take a pause. Think over that. Let me know if you have any questions. Any questions at all? Did it make sense what I was trying to point out? The current source is pointing in the downward direction, so it's opposite of what we expect, what the notation that is given to us, right? The first current was due to the voltage source, it was coming down, so it was positive. Second one, due to the IS voltage, IS current source was pointing up. It's in the opposite direction. So the resulting current is 0. Circuit is at a balance. In reality, there is no current flowing through that resistor or the resistors on the right. There's no current flowing through those resistors on the right. And that is a very short example on superposition. The upside of superposition is that it makes larger circuits easier to analyze. The downside, of course, is that the more number of sources you have in a circuit, the lengthier your analysis gets. If you have 2 sources, you need to analyze 2 times for each single quantity. Here we are only trying to find I2. If you wanted to find the voltage across all 3 resistors, you'd have to analyze them twice for each voltage. If we wish to find the current through each resistor, we need to analyze it twice for, again, the current for each resistor. If you have 3 sources, you have to analyze for each quantity 3 times, and 4 times, 5 times. So as the number of sources keeps on increasing, the time you spend in analyzing the circuit for every single quantity keeps on increasing. Okay, so it's highly inefficient. So it's simple and straightforward, but it's highly inefficient. Does that make sense to everyone? Right? And so superposition, again, is a good technique to apply, maybe to verify your answers if you have the time, but time consuming and highly inefficient. Okay. All right, questions. The steps make sense. Okay. Yes. Okay, so the question being asked is, the only thing we are changing in the circuit is the source. Yes, so yeah, we are not changing it. We are, well, I guess we are changing it, but only for that analysis purpose. That's it. Yeah. We're just analyzing it at one at a time. Because the whole principle is that you have two sources. So the result of the voltage because of those two sources, or the current because of those two sources, is a result of both of those working at the same time. So if we analyze it only one working at a time, we find the value. We analyze with the second one, analyze working at a single time, find the value. Then we sum it together. That's your final answer. And so that's the only thing that we're changing. Yes. Nothing else about the circuit. Also, everyone should keep in mind that we can only reduce an independent source to zero. We cannot reduce a dependent source to zero. If you have dependent sources, they stay as they are. We can't do anything about those. So those will stay as they are. The diamond-shaped dependent sources cannot be reduced to zero. It's an important point to remember. Okay. Okay. If there are no further questions on this topic, then let's move on to one of the most important topics for electric circuit analysis. Okay. Now, next week we'll come back and we're going to look at special cases for node voltage, mesh current, and superposition. We'll solve a few more examples so that students can get practice. Okay. For now, I wish to introduce the topic of equivalent circuits. All right. So let's say you have a linear circuit, right? You don't have to draw this. This is a random example. Okay. This is a completely random example that I just drew out. So let's say you are a designer, you have this kind of circuit, and your boss, your supervisor, your team has tasked you with determining the voltage across R6, which is this resistor on the far right. Okay, so you need to determine VR6. And let's say during this design, all of the other components are already fixed and determined, right? Design means you have a goal, you have an application, and you're trying to design a system, you're trying to create a system that will give you that particular output to fit that application, right? So when you first begin, you might be beginning from scratch. You don't know the value for V1, I1, V3, none of the resistors. But slowly but surely, you try a few combinations and you finally arrive at a circuit where all values are known except for R6. Okay. So now you're trying to find the value for R6. This is a linear circuit, only resistors in there and only independent sources. So what techniques come to mind? Node voltage, mesh current, superposition. Pick any analysis technique you want, generate your equations, you solve them, and you'd find the value for VR6, right? You find the value for R6, and from a value for R6, you will find VR6. Well, it turns out that VR6 is not within compliance. So let's say you need VR6 to be between, I don't know, for instance, 5 and 7 volts, let's say, just random numbers. Okay, that's the requirement. And you choose R6, you perform one iteration of your analysis, you choose R6 to be equal to, I don't know, 100 ohms. And you obtain VR6 as 3 volts, right? So it's not within spec. So you got to perform you pick another value for R6, you perform the analysis all over again. And so second choice for R6, let's say you choose 200 ohms. And not 200, let's say 110 ohms. And now your VR6 is, I don't know, 3.1 volt, let's say. Right? Not much difference. So you have to pick another value. So now you go big. You choose another value. Let's say you choose 300. And this time your value goes, I don't know, 9 volts, let's say. But anyway, the point is you have to perform multiple analyses, multiple calculations to arrive at a single value for R6 that is within your specification range, right? As an engineer, you're going to keep doing this again and again and again and again. Make sense? Well, in order to not do that, there was a French telegraph engineer. His name was Leon Charles Thevenin, way back in the late 1800s. I believe he was a honorary commandant in the French army, and he postulated a theory. And he said, if you have a linear circuit comprising only of linear elements like resistors, and you have independent sources in there, you could represent that entire circuit with one single voltage source and one single resistance. Again, if you have a circuit like this, his postulated theory was you could represent this entire circuit between these terminals as one single voltage source and one single resistor. The voltage source and the resistor would be in series, and they would form two output terminals where R6 would be connected. That theorem came to be named after him, known as Thevenin's theorem. Very well, I won't say popular, but very important theorem for linear circuit analysis. This is not an analysis technique per se. Okay, this is not an analysis technique. This is a theorem where you apply different analysis techniques to derive and reduce your circuit down to one single voltage source. Okay, it's not a new technique. So I want to be clear right off the bat. You're going to take all of the techniques that you've learned and you're going to apply them to determine the value of the single voltage source for this entire circuit and the value of the single resistance. And I cannot stress how important this is because you will keep using this theorem again and again and again and again for the rest of your academic career. Well, even as a practicing engineer, you would need this. So again, I mark this as important. For sure, it's going to be in the final exam. And for sure, you will use it again in 211, you will use it in 212, you'll use it in 306, 307, 308, 409, all of your classes. Okay. Right now, you're only doing this for linear circuits. You'll also do this for AC analysis with vectors, complex math, imaginary number I. And you will see this in 211 and 212. So again, a very important topic. I like to let students know and inform them that these are certain topics that you will see again down the line. Okay, so bookmark this, note this, however you want to note this. It's a very important topic. Okay, so as I said, this was postulated by Thevenin, so it came to be known after him as Thevenin equivalent circuit. This was reducing it to a voltage source. Few decades later, there was a engineer working in Bell Labs, American engineer by the name of Edward Norton, not the actor, he's not that old. He was working with a lot of audio equipment, again, in Bell Labs, working for a lot of audio equipment, telephony. And so it was very convenient for them to use current sources, right? Because you're talking about current moving through the line. And so they were working on a lot of current sources. So based off of Thevenin's theorem, he postulated his own theorem, which was based off of Thevenin's, saying that you could take the same large linear circuit and represent it as a single current source. That theorem came to be known as Norton theorem, named after him, and that circuit is known as Norton equivalent circuit. The form of the circuits are like this. You have a single voltage source in series with a single resistor. Again, single voltage source in series with a resistor between your terminals of analysis. In this particular example, our terminals of analysis are the terminals where R6 was connected. The out plus and out minus have no relevance or significance. Okay, it's nothing. It's just when I was doing the circuit diagram, I had to label the terminals in order for that circuit to work. And so I labeled it as out plus and out minus. It doesn't mean anything. Okay. Nomenclature is random. It may as well be Batman plus and Robin minus. It doesn't really matter. It's A, B, X, Y, whatever you want to call it. Those are the terminals of analysis. We remove R6 from our analysis. We analyze the rest of the circuit without R6, and we represent it as one single voltage source in series with a resistor. If we are talking about Norton equivalent circuit, then we represent it as one single current source in parallel with that single resistor. The terminals of analysis remain the same. Okay. And so these are Thevenin and Norton equivalent circuits, very important, with a capital I and a capital M, a capital P. As an example, let's say you are in 211 next fall, right? Have you all registered, by the way? Not yet? Okay. So you're taking 211 next fall. 211, there'll be a circuit. Let's say you're applying a voltage or current to a capacitor or an inductor, and there are multiple resistors in the way. Well, we have one voltage source and three resistors before we get to the capacitor. The professor, whoever the instructor is going to simply say, okay, remove the capacitor, find the Thevenin circuit of that voltage source and this resistance. And you need to be able to do that within a few minutes. Okay, so you won't be tested separately, but as an electrical engineer, when you're performing circuit analysis, you need to be able to quickly and efficiently reduce a circuit down to its Thevenin or Norton equivalent. And that's how you would encounter this in future courses. All right, so this is, as I was saying, Thevenin and Norton equivalent circuit. These are in series and these are in parallel. Okay, series because only one single connection. The terminals of analysis remain the same. One more thing from here is that the Thevenin circuit is equivalent to this larger one. The Norton circuit is also equivalent to this larger one. So by default, if X equals A and X equals B, it automatically means that A equals B. And so the Thevenin and Norton circuits are equivalent to each other. And from there, we can introduce a concept known as source transformation. Source transformation simply means if you have a voltage source in series with a resistance, you can transform it into a current source in parallel with that same resistance. And the equation that governs it is, anyone? Ohm's law. VTH is equal to IN times RTH. You can transform a Thevenin equivalent circuit to a Norton and vice versa. Okay. All right. All right. Any questions? Okay. A few other points to note on how and why it works is because it's a linear circuit. Linear circuit means, and you reduce it to an equivalent network, means that the voltage at those terminals and the current through those terminals will remain exactly the same for any value of R6, for any value of the load, right? So in this example, In the previous example, the load was R6, right? That is the value of that is the component we are trying to analyze for. So now let's say we determine the Thevenin equivalent network. So we have that entire large circuit represented as VT, sorry, this is RT. Thevenin resistance, this is VT. Oh, by the way, this notations VT, RT, different authors, different books refer to them by different names. Sometimes you might see one book referred to as Thevenin voltage VT. Others might refer to it VTH. Similarly, Thevenin resistance could be represented by single subscript RT or RTH, but that's the same thing. Okay. All right. So now, if you want to find the value for VR6, what can you use? Your large circuit is reduced to one single voltage source in series with a resistor. What can you use now? Absolutely, voltage division. One-step answer, VR6 is your is a fraction of your Thevenin voltage. So it's VT times R6 over the REQ of Thevenin resistance RT and R6, which is simply the sum of RT and R6. No matter how many times you change R6, VR6 is simply a one-step answer. Make sense? Right? You could have a spreadsheet in there, program a million values for R6, you can have a million answers for VR6 within a few seconds. Don't have to calculate or analyze the equations again and again. Okay. Okay. All right. Oh, yeah, the remaining 2 points. Linear network means comprised only of linear elements. Linear elements are resistors, capacitors, inductors. Non-linear elements, you won't encounter them until you take 306, which is diodes, transistors, BJTs, FETs. And then any one-port linear network, one port meaning only has one set of terminals coming out. So any one-port linear network can be represented as a Thevenin or a Norton source or Norton equivalent circuit. Equivalent circuits, nations. Okay, so what I'm going to do is I'm going to stop right here, but I will encourage students, or I will strongly suggest to students to read these 2 slides. Okay, read these 2 slides. Typically, I would not have a lot of words or letters on my slides. It distracts from paying attention to a talk, but these 2 slides are very important, so I have everything in here. So please read these 2 slides before we come to class next Monday. Next Friday. Okay. So we'll end class here today on this slide, and then we'll pick up here again on Friday.